So I have uploaded last. So it seems so far the software works well for recording. It's actually uploading pretty fast too. But I'm still going back and forth on recovering one of the videos that I recorded with that other software. So that will be up when I get to that. So let's get started today. We're starting a new lecture. And that is on imaging techniques. So basically we will review imaging techniques because we have to understand where's the image that we're dealing with and specifically any potential noise coming from. We also have to understand what it is that we can get in the image. So what can we distinguish? We're typically busy distinguishing different types of materials within, and we need to understand, can the technique that we're using, can it actually distinguish what we need it to distinguish? We will focus in this review in general a lot on X-ray and some micromodels, because those are the techniques mostly used around this department. And actually, as part of that, today we are going to go at 1:15 and visit Dr. DiCarlo's scanner downstairs. So we will overview how it works. You also make note that as we visit, these are user facilities that are used. If you think that you could use it for something, you can. It's basically anyone in the department can. So down the line in your research, if you think that imaging something can help you, you let your advisor know. There is some negotiation done then between advisors, but basically for the time, and then you get on a schedule. There's a schedule for these scanners because they're essentially shared facilities. So the one that we will visit is directed by Dr. DiCarlo, so he is in charge of the schedules, right? And there's no doubt that his students are using the most of it, right? That said, everybody in the department is imaging there. And I personally, I don't own that facility, but I co-advise students with Dr. DiCarlo and we image using that X-ray machine. And some of it is in your homework. So I don't know if you looked at that data yet. So again, the principle, so that's going to happen today at 1:15. If somebody could set a timer, that would be fabulous, because I have silenced my phone for a reason. So just wake me up at 1:15 if I don't, or just a little before, because I told Lauren we're going to be downstairs at 1:15. Excellent. So the principal sort of energy source that is used for any type of imaging really is electromagnetic energy spectrum. We know that that spectrum is very wide, goes over numbers of orders of magnitude in wavelengths, for instance. That's often how it's depicted. And that also gives rise to technologically very different imaging solutions, right? So other sources that exist could be acoustic, ultrasonic, electronic. However, electrons have pretty short wavelength and they can see small things, but nothing is transparent to them. And when I say electromagnetic waves can be sort of conceptualized as sinusoidal waves, and that sinusoidal wave has certain wavelength, right? And then the period repeats. Now, all of these probes are sort of like some sort of beams, and they have energy and wavelength of interaction. And depending on what they interact with, they cause it to do something. One part of it could be that I'm passing through. Some of it might be retained in the matter, but there is enough of it transmitting through. Okay? And that's what we need to see through. We know glass, we can see through it. Here, I actually have, so you don't see, you see through this, and then there's some little beads that are actually glass. But there's actually beads that you don't see. Refraction of light. So what happens here is that there's gel beads within. They're larger beads. And there's conceptual porous medium. And there's smooth stuff moving in between through the pore spaces of that. Yes? And then there's stuck. That's what's called strain. Those are the images. It's either by X-ray, so you're going to process for the core. And then down to these strain particles. But here I created a toy with 100 stuff. And transparency of these large beads, they're pretty gels that are hydrated, so they're really water. And because they're water, when I put them in water, I don't see it. Because my light does not get refracted. They have the same index as the water. That's called index matching. Now glass and water, they're both transparent in their own, okay? But they're not index matched. So I'm going to see boundaries of glass because I have light refracted. That's light. Now, this is just to conceptualize. There's straining, there's stuff that gets strained, there's stuff that doesn't. So it's small. We can just kind of go through. This is the same cloth in the porous medium. So you can put that this is just difference of size. But now, this is soy porous media where I managed to make some of it transparent to light. And there are imaging techniques that are making things transparent. If I'm using microscopy, light is going through straight through. And we are using that because there are certain things that shows up in different colors and different materials. We can basically put dye in a material to see different fluids under a microscope. Now, general porous media, this is now glass beads that have been sintered together. It's not transparent. So if I want to see porosity within this, which if glass bead packing, give or take, is between 30 and 40%. Or a sandstone, these things, I don't see through. I can't see through. So we can't use light to image this. We can read in thin section, but then I have to have a very thin sliver. And I can use whether some of the light goes through versus some of it refracts. So that's essentially we are exploring even in this just sort of just thinking about light. Light is an electromagnetic wave with a very short range of wavelengths. You can actually see all of these concepts. Sometimes it goes through, sometimes it refracts a little, and then if you go taking a photograph, it's about, well, can I expose something to my electromagnetic wave and then record this interaction on a different type of image? And that's that image. So that's like sort of like a very crude way of generalizing how all of these things work. So my electromagnetic spectrum here is in the full glory. Visible light is right here. This is what I mean that things are short. That it's a very short range, right? And you can either look at it in terms of wavelength in meters. And here's sort of like a thing that you can that is scaling with that wavelength, right? So if I have houses typically on the order of meters, 5 to 10 meters on a side, right? Baseball is on the order of a decimeter, 10. By the end of the semester, I promise I will get used to my sensitivity of my touchpad. This dot is right here on the order of a millimeter, right? Then cell, then we go to colloidal sizes, bacteria. Viruses are smaller. Yeah? Bacteria I can see under a microscope. Viruses I'm struggling with, right? Seeing. Then we have proteins, water molecules, right? And so forth. So basically the wavelength required to see an object or interact with it must be give or take the same size. Otherwise, I might not have the interaction that I might expect. So that's why everything kind of interacts with electron. Electron is so small. So what type of exercise? So here I have the name or common names of the waves. So visible light is right here. Right? Then have the ultraviolet, infrared light, microwaves, radio waves, X-rays are right here. So what do I need to see a water molecule? Hard X-rays, right? So, and smaller, right? So that's, we have to think about that. Now, this is the sources of all of these waves. People are source of infrared. So that's, if you remember those motion cameras that are infrared, they record motions of objects and stuff like that. Light is right here. It's the source of the light. ALS is the imaging facility near Chicago. So this is the source of the X-rays. X-ray machines are here as well. So some of them fit into the room. That's what we're going to see downstairs. Some of them don't. The perimeter of this is a kilometer, right, of different beams, but you're basically accelerating electrons on a perimeter of a kilometer, and they're emitting X-rays of certain range that you can then, like in different stations along that perimeter, users are using those X-rays. We're going to see that. So, and then radioactive elements have gamma rays. So in terms of porous media, what am I using gamma rays for? Well logs. What a lot of gamma ray radiation, what is identified by high values of gamma shales. So shales have radioactive elements. And we use that, for instance, that's just emission of them. So they have radioactive elements that we can recognize on a gamma ray rock. Okay? And then radio here, well, we're not going to go into porous media. Is not studied in this range. Okay? So again, principle of light is transparency to light. So going through, light has to go through, and I have some examples floating around. Principle of an electron microscope is that you shoot a beam, okay, and then it scatters, and you're recording that scatter. Okay? So scanning electron microscope is recording a scatter of electrons over, did I say that I promised by the end of the semester? Okay, hold me to that. So basically, you shoot a beam and you detect scattered electrons, and that scatter allows you to see details in texture. Okay, so this is oh goodness. So this is radiolaria. They're critters that have this very elaborate shells. They're a fraction of a millimeter. You can see details of those shells because electrons are actually probing inside and coming out. But if you look deeper, you will see a different scatter than from those that scattered off the shell surfaces. And this is what we use in polished sections of the porous media as well. We're going to get to that. So ACM is used quite a bit. Whereas if you look at the optical microscopy, where you're just going through what went through, you don't see those details from the surface. You're just kind of recording what got transmitted. Both can be useful in sizing up this. Its shape, I can use both. But if I need technical information, In porous media, because of all these surfaces, so if you're actually interested in the porous spaces within this, which is what we are after, then it's extremely hard to use unless you figure out a way for some of it to be transparent. So that's something to think about. So opacity, just in terms of terminology, is basically the opposite of transparency, so it's not permitting the passage of it. You could be opaque to any type of electromagnetic radiation. For the most part, depending on electromagnetic wave and its wavelength, you're opaque to some of it often, not to all of it, right? And then you could also attenuate light, and how much you actually absorb depends again on the wavelength of what's passing through and any kind of scatter. So the wave could either pass through, get partially absorbed by the matter, hopefully not changed by it, okay, or some of it could scatter off. Now, if you have, I want to plant that seed immediately in your mind. So whenever you have porous media, such as the one floating around, you have a lot of surfaces within, whether you see them or not. Okay? Even when you look at the stuff that is supposedly opaque, that is supposedly completely transparent, if you actually look, you actually see kind of shades of these spheres. Some of it. So not all of it transmits through because these are curved surfaces. Some of it will reflect back a little. And it's that reflection that we kind of see the surfaces. Kind of see that there is something in there. So some of it always scatters a little. Some of it always comes back a little. And some of it goes through. And that's what also gives rise to different type of noise in the images, because if your models don't capture it correctly, how much of it scatters, how much of it goes through, then it becomes problematic. Enter porous media, you have a lot of surfaces, those surfaces are complex. And you have a lot of materials within the solid phase. You don't have this one nice, glass beads are beautiful, they're just glass, right? They're, give or take, you can make them pretty much 100% quartz. Okay? That's not the case with the regular rock that comes by, and we are not in charge of what is that regular rock that comes by. We just come after the whole rock formation, and we measure then what is the mineralogy, but that mineralogy does affect how we image. Okay? So optical images relies on the ability to illuminate some object and collect and analyze the light it scatters or transmits. If no light is transmitted through an object by whatever electromagnetic wave of a certain energy and wavelength, we cannot image that object with that type of light. Okay? Or I use electromagnetic wave and light interchangeably, though light typically refers to just the visible spectrum of the electromagnetic waves. Okay. Now in porous media, we have different methods that we refer to as 2D methods versus 3D methods. 2D methods are typically destructive in some shape or form. You have to either create a thin section that you can actually use light on, or it's transparent in some way, such as micromodel studies. Okay? And then we use light microscopy. We could also image correlation based on tracking methods. So basically, we will get to that. This is for velocimetry. If I had something moving within the micromodel, I could put little objects. They're not going to be glass spheres, but they are fluorescing elements that I can then track within my micromodel. And those are, and then I correlate to, like, as it moves through, I image again, and difference between the two gives me how much they have moved through, and I can measure velocity. So those are velocimetry methods. Now, 3D methods, these methods can be done in 3D if the porous medium itself is transparent, just like in those glasses. So, Javier, you're a little late. Play with those. You have transparent gel beads, and then there's glass moving through. This is some of the porous medium here is transparent, which in reality we never have, but some of the models, those we refer to as models, basically make solid transparent so I can monitor what's going on in the pore space. All right, and that's basically the model. The one behind you, they're related to the homework problem where there's an X-ray image of smaller beads going through a model like the sintered model, like the one he's holding. So X-ray of that is in your homework. And they're measuring straining. Straining is when beads are large enough so they get stuck. That's that other transparent model, that glass jar. So you can look at what happens when particles are smaller versus larger in terms of straining. That's a fun thing to play with. But that basically explains what is in your homework. That's it. All right. Now, in other 3D methods, there's confocal laser scanning microscopy. So you can zoom in with a microscope. You do need transparency or light going through the medium, but you can zoom in on a plane within the medium. Okay. And these days, it used to be that you just zoom in on one plane. That's it. You zoomed in on one plane and you're looking at 2D image of it. Nowadays, you zoom in, move over, zoom in, move over. You take images, you go through, and you can actually align these images into a 3D image. So confocal microscopy in my lifetime has moved from 2D to 3D. Okay? And then magnetic resonance microscopy and nuclear magnetic resonance. It has somewhat limited resolution. We will get to it too. FIB, focus ion beam, SCM. Focus ion beam is basically, so if I had an SCM, and we're going to get to that, you have to kind of get a surface and then image it. What focused ion beam part is doing is basically it's shaving off a layer of material, then imaging with SCM, then shaving off another layer. And when I say shaving off, it's 50 to 100 nanometer or even less. Okay? Nanometer. Okay? So you can shave off these nanometer scale layers, image, and then assemble that into a 3D image. Okay? So it's obviously destructive. With all of these, we will get to that, but I'm kind of pointing things out ahead, especially since I have all of them on the same slide, is that more you zoom in, your field of view is smaller overall. The size of the overall object you can capture is smaller, the finer the resolution. And that is typically the problem with the thing. Then we have transmission, and apparently I don't know how to spell transmission. And after using these slides for so many years, this is the first time I actually noticed transmission electron microscopy, TEM. It's also a type of tomography, but you have such a thin layer that basically you're going through and your electron beam doesn't scatter as much. And neutron radiography and tomography, you need a nuclear reactor for those, so it's not as common. And computed tomography has a smiley because we have it kind of all over the place in this department. Okay. So thin sectioning is probably to date still the most common petrography method, and it's also used in petroleum engineering. It's a standard method of like going through basically all of the core or the drill cuttings in a well and do the thin sections of them. So you do literally a thin layer of rock and you put it in between two glass plates, and then you use polarizing light to actually image. Now, different minerals will have these different optical properties, and that results in this color and intensity that you see in the resulting image. Okay? So there is like a photomicrograph of a volcanic sand grain. So it's a single grain, but you can see the different mineralogy within that grain. This is plane polarized light and cross polarized light. Okay? And the scale box right here is in millimeters. So this is 0.25 millimeters. Okay? So you will see different things depending on different type of light that you're using. And this is it's a thin glass, right? That has a thin section in between. I actually have a box of those in my office. I'll bring them next time. Micromodels are used in quite a number of groups around this department. Danny, do you know if you're going to work with micromodels or just core flats? Okay. Well, there are people in Dr. Nguyen's group who are working with micromodels. Also, the research groups of Dr. Mohanty and Balhoff use this quite extensively, and now Dr. Wensong as well. Okay. And we can comment on that, but she's basically most often here, I will have what's called a microfluidic chip. Within that chip, what you do is you take a glass and then you etch it with acid. How long you expose it to something, it's going to start, that acid will start etching into the glass. Now, basically what you put, whatever it is that you want to etch, you create a mask. And then the acid will react with only non-masked portions, okay? And not react with the masked ones. And the shape of the masked regions give you the shape of your little columns. Here, the shapes are circular, basically like circular or disc-shaped grains. And then you have certain depth to it. And then you put another piece of glass on top. And you can inject fluids from one end and to the other. And basically, you can control what you inject. It's very small amounts. We're talking milliliters. Right? So you do have to be able to control what you inject and measure it. But this is like, imagine like a mini core flood through this microfluidic device. Right? So basically, this looks like just standard. Like if you put the core here, you would get the same thing. It's just the range of pressures and the range of volumes that you're injecting are different compared to core flood because they scale with the pore volume that you can contain within here. Now, this is the classical setup where you actually have just etched glass. And your model is then glass, it's quartz, it's water wet. Right? So it's sort of reminiscent of sandstone that is mostly quartz. This template, these days, you can actually go and order the template. So you basically draw it in whatever software, or we can create these images. You give them an image that we will be busy creating in this, like the cross section of anything. You can just kind of create a 0-1 image where you want your mask to be and not to be. And then you send to company an image and they give you back a micromodel or this mask that you can then use to etch. It does take a moment to produce one. And you have to be in clean room because this is sizes that are very small. What is the depth of this etching depends on how long you expose. And then you have to put this, you have to basically seal your micromodel on top. But that's something that could altogether take about 10 to 12 hours. So if you're thinking of signing up for a research project like that, have that in mind. So it can be, but then you can also produce multiple versions of it, right? And good thing about these is that they're models, they're reproducible, right? So you can create yourself 10 of them and then use them in 10 different ways and study. And then you put this piece under microscope and you create a video of what's going on. So in that sense, this started in 1952. Our initial understanding of pore scale mechanisms in 2- and 3-phase flow basically comes from micromodels. Are they the same as 3-dimensional media? No. They're actually overly simplistic, to be able to percolate from one side to another, you typically have to have porosities that are like 50 and 60%. I don't know many sandstones that are 50 or 60% porous. That notwithstanding, I'm going to repeat again, our initial understanding of the pore scale mechanisms, how one fluid displaces the other, comes from these two-dimensional models. That was ability to see them is also ability then to explain. So they're nevertheless very valuable, even though they're very simplified, and it's kind of a little, you're going to do core floods, right? So it's, sometimes you do the same experiment, same fluid in a micromodal and in a core flood in a sandstone or a sandpack, and they just don't behave the same because of the third dimension that you have in a larger medium. That notwithstanding, you can still see basic mechanisms in this 2D model. So in terms of research, they're very valuable. And anything and everything, there's vast literature. So whatever the flow mechanism you're interested in studying, well, you can set up a microfluidic experiment and look at it. So reactive flow, EOR, microbial studies, whatnot. Okay? So in Dr. Nguyen's group here, you will have a lot of focus on what do foams do in this type of models. In Dr. Balhoff's and Dr. Mohanty's standard EOR, chemical EOR, different types of it. So they're also used because they're much quicker and smaller amounts of fluids compared to core floods. You can do quick screening of your polymers that you're going to use in EOR and so forth. So microbial studies, we don't have in this around here a lot of microbial studies, not at this university, but our friends in chemical engineering, not in chemical, in environmental engineering, Dr. Charlie Worth could, right? So there's all these different types of studies. Dr. Wen Song, who joined recently, what she specializes in is functionalizing these surfaces and studying reactive flow. So you can functionalize this to be something reminiscent of a quartz or a calcite and so forth, and then calcite will react with different acids differently and so forth. So you can even functionalize it to be clay-like, okay? And then you can monitor what's happening to your two-phase flow displacement, for instance, in this reactive environment. So those are different types of specializations we have in the department. And then if you walk over to environmental engineering, Dr. Charlie Worth, there to my knowledge, uses this, then you're going to have a lot of colloidal studies. What happens if you inject this and that colloid in there or a pathogen, right? So environmental engineering is often concerned with how do pathogens move through a watershed, and these models are then useful in studying that. Okay? Now, we also have this is Dr. Balhoff and Verden, have scaled these down to nanomodels, but it's you can't use regular microscopy anymore to study them. You have to go to SEM, and it's hilariously difficult just to create your nanoscale model and etch these channels that are nanometers wide or 10 or 200 nanometers wide as opposed to 10 to 100 micrometers. 1,000 times difference. Okay? So some of the recent reviews and new ideas in this world. So basically there are 2 review papers if you're interested in learning more. There is a review from 2012. This is a group from Delft. Then there is for EOR applications, there's Gogoy and Gogoy in 2019. JPT recently had an open source kit for micromodel generation, so how to generate. I did not go into details, but basically it's sort of like a MATLAB thing for generating the mask and then sending it off. And so I think it's basically kit for creating this mask, and then you can outsource making mask somewhere else. And so, whoa. What was that? And some recent ideas. So there was velocimetry in micromodels. This is work from Stanford. This is work from our department, so-called 2.5D models. So classical micro model. Whoa, look at that. Classical micro model has sort of like a depth to it that is fixed. If you want to look at trapping of fluids, fixed depth will not do much to trapping. So you have to vary the cross sections in this cross direction as well in order to enhance trapping. So trapping will happen, but very little of it. So those are called that have varied depth. So basically depths, you could have a depth of 20 micron here, and in the middle here 50 micron, right? And that would create this 2.5D model. That's basically the Dr. Bauhoff's group here has. And then there was so-called process-based micro models, where basically you play with different layers of, so you identify images of sand grains, and you create micro models by basically eroding the surfaces of grains. And we're going to play with that once we start manipulating images a little more. So you will learn actually how to do this. Okay? So you can create a slice of sandstone and post-process it to create yourself a micro model that resembles that sandstone. It just has to have a larger porosity in order to actually percolate through it. And then if you want to use look at the YouTube video on functionalized surfaces by Dr. Song, this is our professor, this is Tony Kovchuk is professor in Stanford, then you can take a look at this YouTube video for just like ideas what happens if you have these reactive surfaces. Right? So this is one idea with this process-based micromodels. If you manipulate images, and by the end of this course you're going to be good at manipulating images, so you can create yourself a model medium. And so you can basically process different parts of image to create a layered model. So certain parts of your image here have larger grains or smaller, so larger grains, smaller grains, so more porosity, less porosity, right? So you can create bands of this just by playing with an image and then creating a micro model that resembles that. So you can sort of, if you're looking at trapping or something of that sort, you can actually then see what does a layered type of medium, which most of the time we have in practice basically, what does it do to whatever process you want to look at. You might be looking into foams and you want to look at what's happening to the foam quality. That's the size of the bubbles of the foam that typically as you're passing through, foam will change size. You could look at the displacement of two fluids, right? You can do a lot of things now, depending on what mechanism you want to study. Okay? You could basically dissolve part of it and create a bug. You'll have a 3D version in whatever you're going to be processing for homework. Right? So in this image, this internet defect, actually there is a bug inside. And he put a piece of plaster that he dissolved later. Again, I want to spark your imagination because depending on what you do for research, you can either manipulate images and create yourself controlled porous media that you can repeatedly simulate in to see what different mechanisms, how mechanisms differ depending on the geometry. Or you can create a sintered three-dimensional model, or you could create a minor model, or you can manipulate sometimes to create models. And that way you can study something in a controlled way. Otherwise, you have to have a piece of rock. Let's say that you want to study something, how something changes with porosity. Well, you have to have an example, same type of sandstone in different porosities, which might be difficult thing to do. Okay? So that's just to spark your imagination a little. This is relatively easy to play with if you're in this type of. And then you can also, well, just destroy some of it and create a fracture within your micromodel. Okay. All right. So velocity measurements. We are going to 1:15. So we're gonna go get introduced to X-rays, X-ray imaging downstairs. That's gonna be our first visit. Javier, you're working in a micro city, right? So we're gonna arrange a visit with you next time, if that's a possibility. Right? Can you walk us through? Sure. All right. So next time. So today we will go see Lauren Churchwell. She's waiting for us in the lab, and then that's gonna be medical CT. And then next time we can do